Today, we are looking at the ISO 33771 Single Edge Tear Test, commonly known as the trouser tear. Our goal is to perfectly measure the tear strength of a leather sample. To execute this protocol, you need exactly 3 tools: a Class II tensile testing machine, an ISO-compliant press knife, and a standard thickness gauge. Throughout this process, we will navigate around 3 common failure points: improper sampling orientation, misaligned jaw clamping, and mathematical errors during graph analysis. Adhering strictly to these procedures yields valid, universally recognized data that you can rely on for your quality assurance logging. Step 1 is extraction. We need to cut specific trouser-shaped test pieces from our main leather hide. This animated diagram shows the layout of a leather hide. We must extract exactly 6 pieces. 3 of these cutouts are aligned with their long edges parallel to the hide's central backbone line, and the remaining 3 are cut perpendicular to that line. Once cut, all 6 pieces must be conditioned in a controlled atmosphere, following the exact parameters of ISO 2419. Before loading any piece into the machine, take your thickness gauge and record the exact measurement for each individual sample. Leather has natural directional variations in its structure. Testing along both the parallel and perpendicular axes is the only way to capture the data required to calculate an accurate average tear load. With our samples ready, we move to the machine. Set the initial distance between the upper and lower jaws to exactly 50 millimeters and program the separation speed for a steady 100 millimeters per minute. Take your first trouser-shaped sample and secure approximately 20 millimeters of one leg directly into the lower jaw. The second leg requires a specific geometry. Fold it precisely 180 degrees upwards, back on itself, and clamp it into the upper jaw. Check your alignment carefully. The long outer edges of the leather piece must sit perfectly parallel to the vertical path the machine will travel. Now start the machine. Let it run until the leather is completely torn apart, and make sure to save the resulting force extension plot. If the sample is twisted or clamped off axis, the pulling motion will create localized stress fractures in the material instead of a clean tear, rendering your data completely useless. Now we analyze the data. When looking at your generated force extension plot, do not simply take a mathematical average of the entire recorded line. This line graph plots the jagged peaks of force applied over the extension distance. First, identify the total peak trace area, starting strictly from the first recorded peak and ending at the very last one. Next, divide that entire peak trace area into 4 exactly equal horizontal sections. We strictly discard the first and last quadrants. Remove them from your data pool entirely. Focus only on the 2 remaining middle sections. Within those boundaries, locate and log the 2 absolute highest peaks and the 2 absolute lowest peaks. To qualify as a valid peak, the data point must show at least a 10% rise in force leading up to it and a 10% drop in force immediately after. Take those 4 specific peaks and calculate their arithmetic mean in newtons. Discarding the outer quarters systematically eliminates the initial mechanical slack of the pole and the final terminal rupture of the material. This leaves us with an isolated, accurate measurement of the material's steady-state tear strength. We've now torn and calculated the results for all 6 samples, both the parallel and the perpendicular cuts. It's time to finalize the paperwork. Your final test report must include 4 core mathematical values: the individual leather thickness, the parallel mean tear load, the perpendicular mean tear load, and the total arithmetic average of those directional loads. Finally, document the specific atmospheric conditioning variables that were present prior to the physical testing. A properly populated report proves that the protocol was followed precisely. You have successfully converted raw mechanical force into reliable quality control data.